Hello all. In this video we are going to discuss low energy reaction kinematics of nuclear reaction. This is a nucleus which will be bombarded by very high energy particles. Those particles are called projectile. This nucleus is stationary, so it has zero kinetic energy and it has a rest mass mx. This is called parent nucleus. Parent nucleus will be represented by the capital letter X. And this is a particle which will travel with a very high speed and thus having a very high kinetic energy kx, and it will collide with this nucleus and certain nuclear reaction will take place. This particle collides with the nucleus and the nuclear reaction takes place, and after the nuclear reaction a new nucleus is formed. It is called daughter nucleus. It has a mass my and kinetic energy ky. Daughter nucleus does have certain kinetic energy, and along with the daughter nucleus an escaping particle is formed which travel with certain velocity and has a kinetic energy ky. My is the mass of this escaping particle and ky is the kinetic energy of it. This escaping particle is called outgoing particle. So this is a typical picture of nuclear reaction in which a parent nucleus is bombarded by high energy particles called projectile. Projectile have kinetic energy kx and mass mx. These masses are the rest masses of these particles. After the collision, nuclear reaction takes place and escaping particle and daughter nucleus is formed. We shall consider the nuclear reactions in which the velocity involved are much smaller than the speed of light, so that we can ignore any relativistic effect. So in low energy kinematics, the velocities of particles involved in the nuclear reaction are much smaller as compared to the speed of light. There are two forms of energy involved in a nuclear reaction. Not during the nuclear reaction, but we will be considering the picture well before the nuclear reaction and well after the nuclear reaction. This is because before the nuclear reaction, the projectile particle and parent nucleus are sufficiently far away from each other so that the forces between them are negligible and there is no potential energy. So there are only two forms of energy. One is the kinetic energy of the particles and the other energy is the one associated with their rest masses according to the theory of relativity. So before the nuclear reaction there are two types of energy, kinetic energy and mass energy, and after the nuclear reaction when the escaping or outgoing particle and the daughter nucleus are sufficiently far away from each other, then also we have a kinetic energy and mass energy. No potential energy will be involved, but the potential energy involved during the nuclear reaction, because during the nuclear reaction some complicated interaction involving very strong nuclear forces occur, and those interactions involve potential energy, but we need not consider the potential energy in our analysis because we are considering the picture well before the nuclear reaction and that well after the nuclear reaction. This picture also help us understand most of the information about the nuclear reaction, because well before the nuclear reaction or well after the nuclear reaction, or maybe it is the situation during the nuclear reaction, in all the situations there is one principle that always apply, and that principle is the energy conservation. So we shall use energy conservation principle and then we'll try to describe how energy changes occur during in a given nuclear reaction. As we know that the mass energy is given by famous Einstein equation E equal to mc square, where m is the mass of an object and c is the speed of light. So an object or a material of any object of mass m has an energy E equal to mc square. So we write down the statement of energy conservation. Total energy before reaction is equal to total energy after reaction. What is the total energy before reaction? It is the sum of kinetic energies and mass energies of reacting particles. The reacting particles are the projectile and parent nucleus. So this is the total energy of projectile which collides with the parent nucleus. This is the mass energy and this is kinetic energy of the projectile, and mass energy of daughter nucleus, and this is the kinetic energy of parent nucleus. So this is the total energy before reaction, which is simply the sum of kinetic energies and mass energies of reacting particles. This total energy before reaction is equal to the total energy after the reaction. After the reaction, a new nucleus is formed called daughter nucleus, and it has a mass energy myc square and kinetic energy ky. An outgoing particle is formed which has a mass energy and the kinetic energy. Target nucleus is stationary, so it has zero kinetic energy. Kx will be 0, and we rewrite this equation with Kx equal to 0. Now we take all mass energy terms on one side and kinetic energy terms on the other side. It is a simple algebra. Now we define a Q value, which is a characteristic value associated with a nuclear reaction. We define Q value to be difference in the mass energy of reacting particle and product particle. So this represents the rest masses of reacting particle. This multiplied with c square is the mass energy of reacting particle. These are the masses of product particle, the daughter nucleus and outgoing particle. Its product with the c square represent the mass energies of product particles. The difference between the mass energies of reacting particles and product particles is defined to be a Q value. And from this equation, we see that this represents the difference in the mass energy of reacting particle and product particle, and it is indeed equal to the difference in their kinetic energy. So Q value is also equal to the difference in the kinetic energies of particles in the nuclear reaction. As we see from these equations that our analysis consists of rest masses of all particles and their kinetic energy. A daughter nucleus is much heavier as compared to the outgoing particle formed after the nuclear reaction. So daughter nucleus shows very little motion. It travels very slowly because of being heavy, much heavier than the outgoing particle. So because of its slow motion, its kinetic energy is very small and it is difficult to measure experimentally. So we shall prefer to eliminate the kinetic energy of daughter nucleus from our analysis. Now how do we eliminate the kinetic energy of daughter nucleus from our analysis? This is the topic of next section. We shall eliminate ky from our analysis because it is difficult to measure, and we do this as follows. After eliminating the kinetic energy of daughter nucleus, we get new equation. That equation is called Q equation. We obtain Q equation by employing another conservation principle. We must have other equations involving the kinetic energy of daughter nucleus, and using that other equations we can eliminate the kinetic energy of daughter nucleus from our analysis by simultaneously solving them. So the other equation will be provided by another conservation principle, and that is the principle of conservation of momentum. So again we look at the reaction of these particles. Parent nucleus, and this is a projectile. The collision occurs, nuclear reaction takes place, a daughter nucleus is formed, and an outgoing particle escapes with some kinetic energy. We see that the daughter nucleus and outgoing particle need not travel along the same direction, the direction same as the previous direction, but they may fly off in the different direction. This is the daughter nucleus travel in this direction, and outgoing particle travel in this direction. So they make certain angle with the direction of projectile. projectile particle. This is the direction of projectile particle and these are the directions of product particle. Let's call this direction the longitudinal axis and the direction of motion of projectile is along longitudinal axis. The momentum of the projectile is Px equal to square root of 2mx into kx. We know this formula which relate the momentum and kinetic energy. After the nucleus reaction, the outgoing particle escape in this direction with the momentum Py, making an angle theta with the longitudinal axis or with the direction of projectile. The daughter nucleus travel in this direction, making an angle phi with the direction of projectile particle momentum. Now, both daughter nucleus and outgoing particle have longitudinal component of momentum and transverse component of momentum. The longitudinal momentum component are along the direction of the projectile momentum and transverse momentum component are perpendicular to the longitudinal axis. According to the principle of conservation of momentum, the momentum after the interaction must equal the momentum, total momentum before the interaction. Before the nuclear reaction, the total momentum is just the momentum of projectile because parent nucleus is stationary and has no momentum. So this px represent total momentum before the nuclear reaction, and after the nuclear reaction, py is the momentum of outgoing particle and this is the momentum of daughter nucleus. Before the nuclear reaction, we have momentum only along the longitudinal direction, but after the nuclear reaction, we have momenta along different direction. So if we decompose these momenta in two directions, one the longitudinal direction, another the transverse direction, then longitudinal momenta must equal the momentum of projectile particle and the transverse momenta which were not present before the nuclear reaction. We can see that the projectile does not have transverse momenta, that is the momentum in direction perpendicular to longitudinal axis. So perpendicular momentum do not exist before the nuclear reaction, but they do exist after the nuclear reaction, as you can see. So this transverse momenta after the nuclear reaction must be equal to 0 because there were no transverse momenta before the nuclear reaction, and the longitudinal momenta of product particle must add and equal to the momentum of projectile. This is the principle of conservation of momentum. So if you consider longitudinal momentum of product particle, the longitudinal momentum of escaping particle will be square root of 2 my ky cos theta. This is an angle theta. And the longitudinal momentum of daughter nucleus is 2 my, it is the longitudinal momentum of daughter nucleus. These two longitudinal momenta must add and equal to the momentum of projectile. Longitudinal momenta before the nuclear reaction must equal longitudinal momenta after the nuclear reaction. Now the transverse momenta of product particle. The transverse momenta are for the escaping particle and for the daughter nucleus. These are the transverse momenta. So we have now listed the longitudinal momenta and transverse momenta of product particle. Conservation of momentum. Longitudinal component. The longitudinal momentum before the nuclear reaction must equal the total longitudinal momentum after the nuclear reaction. So this is the conservation of longitudinal momentum. Conservation of longitudinal momentum and transverse momentum can be considered separately. We rewrite this equation. We take the quantity associated with the daughter nucleus on one side of the equation and all the other quantities on the other side. It is a simple algebra. We have taken this on here and we get this new equation. Transverse component. Transverse component, before the nuclear reaction the transverse component was 0, and after the nuclear reaction the transverse component was 2 my ky sin theta plus minus 2my ky sin theta. This represents the transverse momentum after the nuclear reaction. Now, why the negative sign? The negative sign is chosen because the transverse momenta are in opposite direction. Moreover, the angle phi and theta are measured from longitudinal axis in opposite sense. So, this is important to note that the angle phi and theta are measured from longitudinal axis in opposite senses. Theta is measured in anticlockwise direction and phi is measured in a clockwise direction. That's why we have a negative sign here. Had this angle been measured both in the anticlockwise direction, there would be a positive sign in this equation. So when this equation is rearranged, when it is taken on this side, we get this equation for conservation of transverse momentum. I repeat again, theta is measured in anticlockwise direction from longitudinal axis and phi is measured in the clockwise direction from the same longitudinal axis. And because of uh, these ways of measuring the angles theta and phi, we have taken negative sign in that equation. Here we see in these equations the kinetic energy of daughter nucleus is present. In this equation also the kinetic energy of daughter nucleus is present here. So we wish to eliminate kinetic energy of daughter nucleus by using these equations and the Q value of the nuclear reaction that we have seen previously. So there is another variable that is associated with the daughter nucleus and it is the angle at which the nucleus recoil, which is the angle phi. So we first eliminate the angle phi from our analysis and it is easy to eliminate it. We square both sides of this equation and then we add. We get this equation. The right hand side are squared and added and the left hand sides are squared and added and we get this equation. Now here this factor is constant which is related to the daughter nucleus. So that constant factor is taken outside and we get cos square phi and sin square phi inside the bracket and that is simply equal to 1. So in this way we have eliminated the angle phi associated with the daughter nucleus. It is simple to see. And this is equal to 1 and thus the signs thus phi get eliminated. So on left hand side there remains only 2 mk and 2 my ky and on the right hand side we expand this square and some cancellation will lead us to this right hand side. So we use a minus b square formula that is well known to us, a square minus 2ab plus b square. Using this formula the first square is expanded and this is the second square and it is simple matter to see that we finally get this right hand side. We have eliminated the angle phi. Now we have to eliminate another quantity related to the daughter nucleus which is the kinetic energy of daughter nucleus. So how do we remove this kinetic energy of daughter nucleus? It is a simple matter. This second equation is obtained from this equation by dividing both the sides by 2. And now we divide both sides by my and get on the left hand side ky and the other quantities on the right hand side will look like this. Now we have ky equal to this quantity. So on the left hand side we have only ky and on the right hand side we do not have ky. Now we substitute for ky in the q value equation and thereby get ky eliminated from our analysis. We get a new equation in which ky will no longer be present because we will be substituting for ky by this right hand side. We substitute for ky in the q value which we have seen to be equal to kinetic energy of daughter nucleus plus kinetic energy of outgoing particle minus kinetic energy of projectile. We substitute for Ky and get an equation that is free from the kinetic energy of daughter nucleus. We get this equation which does not contain kinetic energy of daughter nucleus, which we wish to bring. And finally, this is an equation. We call this equation the Q value equation that does not contain kinetic energy of daughter nucleus. The Q value equation. During the nuclear reaction, there is sorry, not during the nuclear reaction, but before and after the nuclear reaction, we find that the mass energy and kinetic energy change, and the changes in these forms of kinetic energy are governed by principle of energy conservation. So sometimes the kinetic energy of product particle is greater than the kinetic energy of reacting particle, and sometimes the kinetic energy of product particle is less than the kinetic energy of reacting particles. So there is interconversion between the two forms of energy, the mass energy and kinetic energy. In the situation where the kinetic energy of product particle is greater, it means that mass energy of the reacting particle is partly converted into the kinetic energy of the product particle, and that's why kinetic energy is higher. And when kinetic energy of outgoing particle is smaller, it means that the kinetic energy of reacting particles is consumed and it is converted into mass energy of product particle. Now, there is an interesting phenomena associated with this interconversion between the mass energy and kinetic energy. Depending upon whether the kinetic energy of our product particle is greater or smaller than the kinetic energy of reacting particle, we have classified nuclear reactions into major categories. One is the exothermic or exoergic reaction. In exothermic reaction, the mass energy of reacting particles is converted into kinetic energy of product particles, and thus we have kinetic energy of product particles greater than that of reacting particles, and in this situation the Q value is greater than 0. We know that the Q value is equal to the kinetic energy of product particles minus the kinetic energy of reacting particles. When kinetic energy of product particle is greater than the kinetic energy of reacting particle, which is the energy of projectile only as the daughter nucleus is stationary, then Q value will be greater than 0. And when the kinetic energy of product particle is less than the kinetic energy of reacting particle, there the mass energy is consumed in the nuclear reaction, sorry, kinetic energy of the projectile particle is consumed in the nuclear reaction and converted into mass energy of product particle. So reactions in which kinetic energy of product particle is less than that of the reacting particle is called endothermic or endoergic reaction. I need to correct it. It is endothermic or endoergic. In endothermic reaction, the kinetic energy of projectile is converted into the mass energy of product particle. Therefore, for a given nuclear reaction, the projectile must have a certain minimum kinetic energy for the reaction to take place. Because if the projectile has energy smaller than a certain value, then that kinetic energy may not provide the mass energy of the product particle. For example, if the product particle has certain mass energy, then kinetic energy of the projectile must be greater than the mass energy of mass energy of product particle. If the kinetic energy is not greater than or equal to the mass energy of product particles, then projectile will not be able to provide the energy to form the product particle. So this is the projectile and it has certain kinetic energy kx, and certain mass energy mx into c square, and the kinetic energy converts into the mass energy of product particle. Mass energy of product particle mc square plus my c square. So kinetic energy of projectile needs to be greater than certain value, so that the projectile will have a sufficient amount of energy that can be converted into mass energy of product particle. If the kinetic energy of projectile is smaller than a certain value, then it may not have a sufficient kinetic energy to be converted into the mass energy of product particles. Product particles will not be formed and nuclear reaction will not be taken place. So projectile particle must have certain minimum kinetic energy. Below that kinetic energy, no nuclear reaction will be taken place, because no energy will be available to form product particles with their corresponding mass energy. So the minimum kinetic energy that the projectile must have for the nuclear reaction to take place is called threshold energy of projectile. After the nuclear reaction, the outgoing particle and daughter nucleus have longitudinal velocity component and transverse velocity component. The conservation of total energy occur, and the conservation of momentum also occur. The conservation of longitudinal momentum already determine the longitudinal velocity of the product particle. In addition to the longitudinal velocity, transverse velocity are also transverse velocities are also present. But even if the transverse velocities are not present and only horizontal velocities are present, the momentum conservation is still valid. Momentum conservation is valid even when transverse components are not present. So when transverse components are present, they only provide additional kinetic energy of product particles, additional kinetic energy. And when these transverse components are not present, momentum conservation occur as well as conservation of energy occur. But when transverse components are not present, it corresponds to less kinetic energy of daughter particle or less total energy of daughter particle, and that less total energy of daughter particle correspond in turn to the less kinetic energy of projectile. So when projectile has a minimum kinetic energy, in that situation these product particles will not have transverse velocity components but only the horizontal velocity component, or the product particles will continue to travel in the same direction as that of the projectile particle with the angle theta and phi equal to 0. With the transverse velocity components, only the kinetic energy is added, but that is the extra kinetic energy, and this extra kinetic energy associated with transverse velocity component will simply be 0 in situation where the projectile has minimum kinetic energy required to form the daughter particles with their rest mass energy and kinetic energy. So with the minimum kinetic energy of projectile, one does not have transverse velocity component but only the longitudinal velocity component, in which the angle theta and phi are 0. And this is important to understand that at a minimum kinetic energy of projectile, the angles theta and phi are 0, and this is from where our analysis of threshold kinetic energy begins. At threshold kinetic energy, theta and phi are 0. We substitute theta and phi equal to 0 in the Q value equation we have just derived. This is the Q equation where we substitute theta equal to 0 and get this equation. Cos theta with theta equal to 0 become 1. and we can treat this equation as a quadratic equation in square root of ky. We write this equation like this. We write ky as the square root of ky. This ky is so written. And then we take this ky outside and write it separately. So this is a square of square root of ky, and this is just the square root of ky, and this is the remaining term. So this equation when rewritten like this, we see that this equation resembles the quadratic equation ax square plus bx plus c equal to 0, where x represents square root of ky and a, b, c are the constant coefficients. Now, when the kinetic energy of projectile is at minimum, when kx is at its minimum, means that is the threshold kinetic energy, it is unique. When projectile kinetic energy has a unique value, it corresponds to the unique value of kinetic energies of daughter nucleus and outgoing particle. But kinetic energy of daughter nucleus, which is K capital Y, have been already eliminated from our analysis. So we have only the kinetic energy of outgoing particle in our analysis along with the energies of reacting particles. So kinetic energy of outgoing particle will also be a unique value when the kinetic energy of projectile is at minimum and hence has a unique value. So in this quadratic equation, the unique minimum value of kinetic energy of projectile gives rise to a unique value to the kinetic energy of outgoing particle. It means that this quadratic equation in square root of ky has a unique value or a unique solution. And when a quadratic equation has a unique solution, b square minus 4ac is equal to 0. It is because the solution of quadratic equation is given by uh, minus b plus or minus square root of b square minus 4ac divided by 2a. So it is the value of this term that gives rise to two different values of the solution of this quadratic equation. But when it has a unique solution, when the root is unique, then this b square minus 4ac must be 0, so that x will have a unique value of minus b upon 2a. So b square minus 4ac must be 0, and b square minus 4ac equal to 0 when applied to this quadratic equation in square root of ky will give us this equation. This is the equation we obtain when we apply b square minus 4ac equal to 0 to this equation. Now our further analysis simply involves some algebraic manipulation and which lead to the final expression for the minimum kinetic energy. Just remember that we are considering the situation where kx is minimum and minimum value of kx correspond to a certain unique value of ky, and unique value of square root of ky correspond to b square minus 4ac equal to 0 applied to this equation, giving us this equation. And now kx is the minimum value in this equation. So we have to find this minimum value of kx in terms of the rest of the quantities present in the same equation. So we shall do such algebraic operations that we will have kx on one side of the equation and all the rest of the quantities onto the other side. So our first step will be cross multiplication inside these two brackets, cross multiplication. After the cross multiplication, we will see that in the second term does also have my square in the denominator. So my square in the denominator of the first term and the my square in the denominator of the second term will get cancelled when we multiply both sides by my square. So the following equation is the result of all these algebraic processes we perform. Cross multiply here also cross multiply, and then multiply these two brackets. So after having done all the multiplication, we will get my square in the denominator of the second term, and it is already present in the denominator of the first term. Then we multiply both sides by my square, and we have right hand side 0 again, but on the left hand side we would have removed my square. This leads to the following equation. Now this bracket is multiplied with the terms inside the square bracket, and then the multiplication in square bracket are also performed. So this the bracket outside multiplies with the first term of the square bracket, and it gives us this, and this multiply now with qmy, and it gives us this term, and it is equal to 0. Now this my is multiplied with capital M and then multiplied with small m, and the first two terms are obtained. Then this capital My is now multiplied with this My, it giving us my square, and then multiplied with this mx, giving us this. The kx is outside, this kx is here, and my plus my, it is written as it is. Now this mx my and this mx my get cancelled, and we have this inside the bracket. Here this my and the my from this and my from this are taken common. I repeat, plus mx my minus mx my get cancelled. The my from here and from here is taken common outside. And in bracket, when my is taken common, we will have my here and one capital My and only mx here, because all capital My's are taken outside common. So here also we have my. Then this my we multiply both sides, sorry, we divide both sides of this equation by capital My. When division by capital My is done, the capital My get removed, and we get this equation. So what we have to do? Take My common from the first bracket, and this is the My of the second term, and then divide both sides by My, and it will give us this equation. Now we divide both sides by this factor. Dividing by this factor on both sides, then we will have only kx on one side and minus mx myq on the other side. So this second equation is obtained from the first equation by only dividing by this factor on both the sides. Now the definition of q value. This equation represents the definition of q value, the difference in the mass energies of reacting particles and product particles. We have only taken c square on the left hand side. Now the value of this q by c square, it has the dimension of mass, and this value is much small as compared to the masses of particles in the nuclear reaction: projectile particle, parent nucleus, daughter nucleus, and outgoing particle. So as compared to the masses of reacting particle, this value q upon c square, which has the dimension of mass, is much small, and we can treat it to be nearly 0 and write 0 on the left hand side, and we get this equation. We have taken q by c square as 0 and rewritten this equation. Now from this equation we see that this is equal to this. It is transferred on this side, and we get this new another equation. So capital My plus small my equal mx plus mx. So here in this equation we have mass of daughter nucleus involved. So we substitute for My plus My, which is present here and also here. Here, here and here. It is equal to mx plus mx. Right hand side represent the quantities associated with reacting particles with which we begin our experiment. So quantities associated with the reacting particles are well known to us and we can control them. So we prefer to have final formula, final equation in terms of quantities which we can control and which are well known to us. So we substitute for these quantities associated with uh, product particles, we substitute them by quantities associated with reacting particle using this equation. So mx, the x quantities go in place of y quantities and we get finally this equation for the minimum kinetic energy of projectile. This equation represents minimum kinetic energy of the projectile required to initiate the nuclear reaction, and this is called threshold kinetic energy. We thus have a formula for threshold kinetic energy of projectile. We stop here. Thank you.